Interplanetary space between Earth and Mars exists as a vast region of near vacuum where matter becomes extremely sparse and motion continues without resistance over long distances. Within this region, microscopic particles drift at great separation, and spacecraft travel through an environment that offers almost no physical support. The absence of air eliminates familiar concepts of wind or sound, leaving only the slow progression of objects governed by gravity and inertia. The space between planets is not completely empty, yet the remaining material is spread so thin that collisions between particles are rare over human timescales. Occasional dust grains, ionized atoms, and fragments of solar origin material occupy this region, but they exist at densities far below any terrestrial atmosphere. This extreme dilution creates conditions where light travels unimpeded and temperature is not defined by surrounding air, but by radiation absorbed or emitted by objects. Distance dominates all aspects of this environment. The separation between Earth and Mars changes continuously as both planets follow their orbits around the Sun. At closest approach, the distance still measures tens of millions of kilometers, expanding to many times that value at opposite sides of their orbital paths. A spacecraft moving through this region does not follow a straight line in a simple geometric sense, but instead traces a curved trajectory shaped by gravitational influence from multiple bodies. Gravity remains the primary force shaping motion. The Sun exerts the strongest pull holding planets and spacecraft in extended orbital paths. Earth's gravity gradually loses influence as distance increases, while Mars begins to assert its own gravitational field only when a spacecraft approaches closer to its orbital region. Between these zones, motion becomes a balance of competing gravitational pulls, resulting in smooth transitions rather than abrupt changes in direction or speed. Energy in this region is not carried by air or fluid movement but by radiation and particles moving outward from the Sun. Heat transfer occurs through direct absorption of electromagnetic energy, and surfaces exposed to sunlight warm rapidly, while shaded areas cool just as quickly. This contrast produces a dynamic thermal environment, where temperature depends entirely on orientation and exposure rather than any surrounding medium. A spacecraft traveling through interplanetary space relies on carefully calculated velocity established during launch and adjusted through limited course corrections. Without atmospheric drag, there is no natural slowing, and momentum remains nearly constant unless acted upon by gravitational forces or controlled propulsion. This allows long periods of coasting where the vehicle moves silently and steadily along its trajectory. Navigation in this environment depends on continuous measurement of position relative to known celestial bodies. Even small deviations in velocity can accumulate over time, gradually shifting the projected arrival point by large distances. As a result, trajectory planning requires precise initial conditions and occasional adjustments using onboard systems that provide controlled thrust. The environment also contains faint traces of charged particles that originate from the Sun and distant cosmic sources. These particles move in streams and diffuse flows, filling the space with subtle energetic activity that does not resemble atmospheric weather, but still represents a constant background presence. Their density is low, yet their movement contributes to the broader physical character of interplanetary space. Light from the Sun spreads across this region without obstruction, illuminating spacecraft and dust particles alike. Shadows form sharply in the absence of scattering, creating high contrast between illuminated and unlit surfaces. This clarity of light contributes to the perception of emptiness, as there is no haze or atmospheric diffusion to soften visual boundaries. Time in interplanetary travel is measured not only in hours or days, but also in orbital phases and alignment windows. The journey from Earth to Mars depends on planetary positions that determine energy efficiency and travel duration. These windows occur periodically, shaping when missions can depart and how long they must travel before reaching their destination. Throughout the transit region, structural materials of spacecraft endure continuous exposure to vacuum conditions. Outgassing of trapped molecules, thermal expansion and contraction, and gradual material fatigue occur slowly under these stresses. Engineering designs account for these factors by selecting materials that remain stable across extreme temperature shifts and prolonged isolation. The vastness of this space creates a sense of scale defined not by landmarks, but by reference points separated by immense distance. Even the nearest objects appear fixed against a background that changes only gradually over time. Movement is perceived through comparison, rather than immediate visual cues, reinforcing the slow and continuous nature of interplanetary travel. Within this environment, human presence is indirect, mediated entirely through machines that maintain life support and communication. Signals travel at the speed of light, but still require several minutes to cross the distance between planets. This delay establishes a separation between action and response, where information arrives slowly and consistently, rather than instantaneously. As spacecraft progress further from Earth, the sense of connection shifts toward reliance on pre-programmed systems and autonomous adjustments. Real-time intervention becomes limited by distance, and stability depends on the precision of earlier planning. The interplanetary region thus functions as both a physical pathway and a temporal buffer separating planetary environments while linking them through controlled motion. Radiation fills interplanetary space as a persistent and invisible component of the environment, shaping every stage of travel between Earth and Mars. This radiation originates primarily from the Sun, where continuous nuclear reactions produce energetic particles that stream outward in all directions. Additional contributions come from distant cosmic events, including supernova remnants and high-energy galactic sources, creating a background field that permeates the solar system. The solar wind forms the most immediate and consistent radiation flow. It consists mainly of charged particles such as protons and electrons moving at high velocity through space. This flow is not uniform. It changes with solar activity strengthening during periods of increased solar output and weakening during calmer phases. As it expands outward, it interacts with planetary magnetic fields and any objects within its reach, shaping the plasma environment of interplanetary space. In regions far from strong planetary magnetic protection, these particles move almost unimpeded. Spacecraft traveling through this region encounter a continuous stream of energetic impacts at a microscopic level. Although individual particles are extremely small, their cumulative effect over time becomes significant for both materials and biological systems. Shielding becomes a critical consideration, not as a complete barrier, but as a means of reducing cumulative exposure. Cosmic radiation adds another layer to this environment. Unlike solar particles, cosmic rays originate from outside the solar system and consist of highly energetic atomic nuclei accelerated to extreme speeds by astrophysical processes. These particles are rare compared to solar wind particles, but each carries far greater energy, allowing them to penetrate shielding more deeply and create secondary particle cascades when they interact with matter. The interaction between radiation and spacecraft materials produces gradual structural and chemical changes. Atoms within materials can be displaced from their positions, leading to microscopic defects in metals and composites. Over time, this accumulation of small disruptions can alter mechanical properties, making material selection and long-term durability essential considerations in mission design. Inside, a spacecraft radiation levels are reduced but not eliminated. Shielding materials absorb or deflect a portion of incoming particles, yet high-energy components still penetrate to interior spaces. This creates a continuous low-level exposure environment where protective design must balance mass constraints with effectiveness. Heavier shielding offers greater protection, but increases launch and propulsion demands. Radiation also influences electronic systems. High-energy particles can disturb electrical charges within circuits, causing temporary malfunctions or data corruption. To manage this, systems are designed with redundancy and error correction capabilities, allowing operations to continue even under intermittent disturbances. These safeguards are essential for maintaining stable navigation and communication during long-duration travel. Outside the spacecraft, radiation interacts with the sparse particles of interplanetary space, producing ionization effects that shape plasma behavior. Neutral atoms can be stripped of electrons, becoming charged and responding to magnetic fields. This process contributes to a dynamic but extremely diffuse plasma environment that extends throughout the solar system. The Sun's magnetic field extends far beyond its visible surface, forming a large-scale structure that guides the movement of charged particles. This heliospheric field is shaped by solar rotation and activity cycles, creating regions of varying intensity and direction. Spacecraft passing through these regions encounter changes in particle density and energy distribution, though without the sensation of movement through a fluid medium. Radiation exposure varies depending on shielding orientation and spacecraft position relative to the Sun. Surfaces facing the Sun receive direct energetic input, while shaded areas are influenced more by secondary particles and scattered radiation. This creates subtle gradients across the structure of a spacecraft, influencing thermal and material responses over time. Biological systems are particularly sensitive to this environment. Living tissue exposed to high-energy particles can experience molecular damage at the cellular level. In the absence of Earth's protective atmosphere, and magnetic field exposure accumulates steadily. Understanding this accumulation is essential for evaluating long-duration human presence in deep space. As spacecraft move farther from Earth, communication delays increase, and real-time monitoring of radiation events becomes more challenging. Solar activity can change rapidly, producing bursts of energetic particles that reach spacecraft with limited warning. These events require pre-planned protective responses, often involving temporary sheltering within more heavily shielded sections of the vehicle. Despite its invisibility, radiation defines much of the interplanetary environment. It shapes material behavior, influences system design, and establishes constraints on human activity beyond planetary boundaries. Rather than being an occasional hazard, it forms a constant background condition that must be accounted for in every aspect of travel. Within this context, Mars-bound missions are not only journeys across distance, but also passages through a persistent energetic field that cannot be avoided or fully blocked. Adaptation becomes the primary strategy, relying on engineering, timing, and structural design to reduce cumulative effects rather than eliminate them. Mars orbital space forms a transitional region where the influence of the planet begins to reshape the surrounding environment without fully replacing interplanetary conditions. This region is not sharply defined, but gradually emerges as the gravitational pull of Mars becomes comparable to the weaker influence of the Sun at that distance. Spacecraft entering this area begin to experience subtle shifts in trajectory that reflect the growing dominance of the planet's gravity. The approach to Mars involves a long adjustment phase in which motion is continuously refined. Even before reaching orbit, a spacecraft moves through a region where gravitational forces from both Mars and the Sun interact in a delicate balance. This creates curved paths that must be carefully managed to avoid overshooting or falling too steeply into the planet's atmosphere. Small corrections are applied, gradually reflecting the precision required to transition from interplanetary travel to orbital capture. As distance decreases, Mars grows in apparent size, revealing surface features such as impact basins, volcanic regions, and dust-covered plains. The planet appears muted in color, dominated by shades of red and brown caused by iron-rich minerals in its surface material. This visual change marks a shift in environmental context from deep space emptiness to a defined planetary system with geological structure. The gravitational field of Mars is weaker than Earth's, but still strong enough to establish stable orbits for spacecraft and natural satellites. Entry into orbit requires careful alignment of velocity and angle, ensuring that the spacecraft's momentum is reduced enough for capture without direct atmospheric entry. This process depends on precise timing, as even small errors can lead to escape back into interplanetary space or unintended surface impact. Once captured into orbit, a spacecraft begins to follow a curved path around Mars, circling the planet at varying altitudes depending on mission design. Lower orbits provide closer observation of surface features, but require more frequent adjustments due to atmospheric drag at the upper boundary. Higher orbits offer broader coverage and greater stability, though with reduced spatial resolution for surface observation. Mars orbits are influenced by subtle variations in the planet's mass distribution. Differences in crust density and subsurface structures create minor gravitational anomalies that can slightly alter orbital paths over time. These variations are not large enough to destabilize motion quickly, but they accumulate slowly and must be corrected through occasional propulsion adjustments. The thin atmosphere of Mars extends far above the surface, gradually thinning into near-vacuum conditions. At orbital altitudes, traces of atmospheric particles still exist, particularly during periods of increased solar activity when the atmosphere expands outward. These particles create minimal drag, but over long durations they can still affect orbital stability for low-altitude spacecraft. The transition between interplanetary space and Mars orbit is also marked by changes in plasma environment. The solar wind interacts with the planet's weak magnetic fields and atmospheric remnants, producing a complex region of charged particle behavior. Unlike Earth, Mars does not have a strong global magnetic field, so this interaction is uneven and localized, influenced by crustal magnetic regions, rather than a unified planetary shield. Spacecraft systems operating in Mars orbit must account for this variability. Navigation relies on continuous tracking of position relative to both the planet and distant reference points. Communication with Earth becomes more stable compared to deep space travel, but still involves significant delay due to distance requiring autonomous decision-making for real-time adjustments. Thermal conditions in Mars orbit also differ from interplanetary space. The planet reflects sunlight and emits infrared radiation, creating a more complex thermal environment. Spacecraft surfaces alternate between periods of heating and cooling as they pass in and out of sunlight, requiring carefully designed thermal regulation systems to maintain stability. The visual perspective from Mars orbit provides a slow, continuous view of a rotating planet. Surface features move gradually beneath the spacecraft, revealing cycles of day and night dust movement and seasonal variation. This motion is steady and predictable, governed by the planet's rotation period, which is slightly longer than Earth's. Dust activity on Mars can extend into higher altitudes during large-scale atmospheric events. Fine particles lifted from the surface can reach upper atmospheric layers, where they interact with sunlight and create diffuse atmospheric shading. These events can reduce visibility of surface features from orbit and alter thermal absorption patterns across the planet. Orbital dynamics around Mars are influenced not only by gravity but also by solar radiation pressure. Photons from the Sun exert a small but continuous force on spacecraft surfaces, gradually altering trajectories over time. While minimal in the short term, this effect becomes significant for long-duration missions and must be included in navigational planning. As spacecraft settle into stable orbit, the environment becomes more structured compared to interplanetary space. Reference points are no longer distant stars alone, but include surface landmarks, atmospheric layers, and gravitational gradients. Motion becomes more predictable, yet still requires constant adjustment to maintain stability within this multi-influenced region. Mars orbital space thus represents a threshold zone where deep space travel transitions into planetary interaction. It is a region defined by balance rather than emptiness or solid presence, where forces overlap and motion becomes increasingly complex as proximity increases. Atmospheric entry into Mars begins at the outermost traces of its thin carbon dioxide envelope, where the distinction between space and atmosphere is gradual rather than abrupt. At these extreme altitudes, gas particles are widely separated, and the atmosphere behaves more like a transitional plasma region than a continuous fluid. A spacecraft descending into this layer begins to encounter increasing resistance, though still far weaker than anything experienced in Earth's atmosphere. The initial interaction is defined by high velocity and minimal density. As the spacecraft enters the upper atmospheric boundary, individual gas molecules collide with its surface at extreme speeds, converting kinetic energy into heat at localized points. This process begins heating long before any visible atmospheric compression appears, as energy transfer occurs through rare but high-energy impacts. Mars' atmosphere is composed primarily of carbon dioxide with small amounts of nitrogen and argon. This composition creates a distinct thermal response during entry, as carbon dioxide molecules interact differently with heat compared to nitrogen-oxygen mixtures found on Earth. The low overall density means that aerodynamic braking is weak at first, requiring spacecraft to rely heavily on precise trajectory design to ensure gradual energy dissipation. As descent continues, atmospheric density increases slowly, but remains far below Earth's surface-level conditions even at lower altitudes. This creates a long, extended entry phase where heating builds gradually rather than suddenly. The spacecraft experiences sustained thermal stress distributed across its outer structure, requiring heat shields designed to absorb and radiate energy over extended periods rather than withstand a single peak shock. The thin atmosphere produces limited aerodynamic lift, meaning that control during entry is achieved primarily through careful adjustment of angle and orientation rather than sustained gliding. Even small variations in angle can significantly alter descent path, making precision essential for maintaining a safe trajectory toward the intended landing zone. During this phase, the surrounding air becomes increasingly active at a molecular level. Gas particles compress ahead of the spacecraft, forming a region of increased temperature and density known as a shock layer. In this region, energy is transferred rapidly between moving and stationary particles, producing intense heating at the leading surface while the surrounding atmosphere remains relatively cold. Unlike Earth, Mars does not provide thick atmospheric buffering to distribute this heat. Instead, the energy is concentrated over smaller volumes and shorter timescales, creating sharp thermal gradients across the spacecraft's surface. Heat shields must therefore rely on materials that can undergo controlled erosion or high temperature resistance without structural failure. As the spacecraft descends, further atmospheric drag begins to play a more significant role in reducing velocity. The gradual increase in resistance slows the spacecraft without requiring continuous propulsion. However, because the atmosphere is still thin, this deceleration remains slow compared to Earth entry conditions, extending the duration of exposure to heating effects. The surrounding environment during entry is also influenced by dust suspended in the atmosphere. Fine particles lifted from the surface by winds or global dust activity can extend into higher layers and interact with incoming spacecraft. These particles are extremely small, but can contribute to additional heating and scattering effects as they collide with high-speed airflow around the vehicle. Mars' atmospheric entry is further complicated by seasonal variations. During certain periods, the atmosphere expands slightly, due to increased solar heating raising its upper boundary and altering density profiles at entry altitude. These variations require mission planning to account for differences in drag and heating behavior depending on arrival timing. Communication during entry becomes increasingly limited as plasma forms around the spacecraft due to ionization of atmospheric gases. This ionized layer can temporarily block or distort radio signals, creating a communication blackout phase. During this period, the spacecraft operates autonomously, relying on pre-programmed sequences to guide descent through the most critical phase of atmospheric interaction. The descent path is carefully controlled to balance heating, deceleration, and stability. Too steep an entry angle results in excessive thermal stress, while too shallow an angle risks skipping back into space. This narrow range of acceptable conditions requires precise navigation long before atmospheric contact begins, as adjustments during entry are limited. As altitude decreases further, the atmosphere becomes dense enough to allow more effective aerodynamic control. Surface features begin to influence local wind patterns, though winds remain weak compared to Earth. These winds can still affect landing systems during final descent, requiring compensation for lateral drift and surface variability. The transition from high-altitude entry to lower atmospheric descent marks a shift from thermal dominance to aerodynamic control. Heat remains present but gradually decreases in intensity as velocity is reduced. The spacecraft moves from a state of extreme energy conversion into a more controlled descent phase governed by drag and stabilization systems. Eventually, the spacecraft approaches the boundary between atmospheric flight and surface landing, where the remaining velocity must be carefully reduced to prevent impact damage. This final phase depends on a combination of parachutes, retropropulsion, or other braking systems, each adapted to the thin atmospheric conditions. Mars' atmospheric entry thus represents a prolonged and delicate transition, where space motion is slowly transformed into controlled interaction with a fragile planetary atmosphere. It is a region defined by gradual change where every layer of descent introduces new physical constraints that must be managed continuously. Global dust storm atmospheric dynamics on Mars represent one of the most influential and wide-reaching environmental processes on the planet's surface and lower atmosphere. These events begin locally where wind lifts fine regolith particles from dry regions, but under certain conditions they expand into large-scale systems that can envelop vast portions of the planet. The atmosphere, already thin and dry, becomes filled with suspended dust that gradually alters both visibility and energy balance. Dust on Mars consists of extremely fine particles produced by long-term erosion of basaltic rock. These particles are small enough to remain suspended in the atmosphere for extended periods once lifted. Because gravity is weaker than on Earth, and atmospheric density is low, settling occurs slowly, allowing dust to circulate widely before returning to the surface. This persistence enables storms to grow in both size and duration. The initial phase of a dust storm begins near the surface, often triggered by localized wind systems driven by temperature differences. As sunlight heats the ground unevenly, air rises in warmer regions and descends in cooler ones, creating circulation patterns. These movements generate surface winds capable of lifting dust into the atmosphere, especially in regions where fine sediment is abundant. Once dust enters suspension, it interacts strongly with sunlight. The particles scatter and absorb incoming radiation, reducing the amount of direct sunlight reaching the surface. This leads to localized cooling of the ground, while the atmosphere above becomes warmer due to absorbed energy. This shift in temperature gradients can further modify wind patterns, reinforcing the circulation that keeps dust aloft. As storms expand, they can merge with other active regions, forming regional systems that gradually extend across hemispheres. During large-scale events, dust can spread across the entire planet, creating a global haze that obscures surface features when observed from orbit. These global dust storms can persist for weeks or even months depending on atmospheric stability and seasonal conditions. The vertical structure of dust storms extends far above the surface. Fine particles can reach into the upper atmosphere, where lower pressure allows them to remain suspended even more easily. At these altitudes, dust interacts more directly with solar radiation, influencing the thermal structure of the entire atmosphere. This can lead to warming of higher layers while cooling the surface below. The energy balance of Mars is strongly affected during these events. With sunlight partially blocked from reaching the ground, surface temperatures drop sometimes significantly. At the same time, atmospheric heating increases due to absorbed radiation. This redistribution of energy alters circulation patterns and can sustain storm activity even after initial lifting mechanisms weaken. Dust storms also influence atmospheric density at higher altitudes. As particles heat and expand the air around them, the upper atmosphere can temporarily increase in thickness. This affects spacecraft orbiting the planet, as increased atmospheric drag at very low orbital altitudes may occur during strong storm periods. These changes are subtle but measurable over time. Surface visibility during a global dust storm becomes extremely limited. The horizon appears muted and diffuse, with light scattered in multiple directions by suspended particles. Direct shadows weaken, and contrast between surface features decreases significantly. From orbit, the planet appears enveloped in a uniform reddish haze, with surface details partially or fully obscured. Despite their dramatic appearance, dust storms do not involve liquid water or precipitation. They are entirely driven by dry atmospheric dynamics and particle suspension. The absence of moisture means that particles remain free to move without aggregation, contributing to the long duration and wide coverage of these events. The seasonal cycle of Mars plays a role in dust storm formation. During periods when the planet is closer to the Sun, increased solar heating can intensify atmospheric activity, raising the likelihood of large-scale storms. However, not all close approaches result in global events, indicating that additional atmospheric and surface conditions must align for full planetary coverage to occur. Dust storms also interact with the planet's weak and irregular magnetic environment. While Mars lacks a global magnetic field, localized crustal magnetic regions can influence charged dust particles at a very small scale. These effects are minor compared to aerodynamic forces, but contribute to subtle variations in particle motion in certain regions. For spacecraft and surface systems, dust represents both a physical and operational challenge. Accumulated dust on solar panels reduces energy efficiency, while suspended particles can affect optical instruments and thermal regulation. These impacts occur gradually during storms and require systems designed for resilience and periodic recovery. Atmospheric circulation during global dust storms becomes more uniform as temperature differences between regions decrease. With sunlight reduced at the surface, the driving force for local convection weakens, but large-scale atmospheric motion continues due to residual thermal gradients and planetary rotation. This creates a more homogenized but still active atmospheric system. Even after dust begins to settle, residual effects persist in the atmosphere. Fine particles can remain suspended at high altitudes long after surface conditions stabilize, continuing to influence light scattering and thermal balance. The return to clear conditions is gradual, reflecting the slow dynamics of particle removal in a low-density atmosphere. Mars dust storms therefore represent a planetary-scale redistribution of surface material into the atmosphere driven entirely by wind temperature and particle dynamics. They reshape the visual and physical character of the planet, temporarily demonstrating how even a thin atmosphere can produce large and persistent environmental systems. The Martian surface exists as an exposed, unshielded boundary where radiation from space interacts directly with soil, rock, and any structures placed upon it. With no global magnetic field and an atmosphere too thin to provide meaningful protection, high-energy particles from the Sun and deep space reach the ground with far greater intensity than on Earth. This constant exposure defines the surface environment as one of persistent energetic bombardment, rather than atmospheric shielding. Cosmic rays and solar energetic particles penetrate the upper layers of the surface and interact with regolith at a microscopic level. These interactions produce secondary particles that spread energy through surrounding material. Over time, this process leads to gradual changes in the chemical and structural properties of exposed soil and rock. The effects are subtle at short timescales, but accumulate continuously over years and centuries. The surface material known as regolith consists of finely broken rock formed through long-term impacts, erosion, and thermal stress. Unlike Earth soil, it contains no organic rich structure and is dominated by oxidized minerals, particularly iron compounds that give Mars its characteristic reddish color. These minerals have been altered over time by exposure to radiation and atmospheric chemistry, creating a surface layer that is chemically reactive under certain conditions. Radiation reaching the surface does not remain uniform in its effects. Variations in particle energy angle of incidence and local shielding by terrain features create uneven exposure patterns. Slight depressions, rock overhangs, and dust accumulations can reduce direct exposure, while open plains receive full intensity. This produces a patchwork of radiation environments across the landscape. Temperature extremes on the surface further interact with radiation effects. During daylight, sunlight warms exposed ground, while at night rapid radiative cooling causes temperatures to drop sharply. This cycle of heating and cooling contributes to mechanical stress in surface materials, gradually breaking down rock into finer particles that are more easily transported by wind. The combination of radiation and temperature variation creates a slow but continuous transformation of surface chemistry. Perchlorate compounds, which are naturally present in Martian soil, are influenced by these conditions and contribute to the oxidative environment. These compounds remain stable under current conditions but become chemically active when exposed to certain environmental triggers, affecting potential material stability. Biological implications of surface radiation are significant in discussions of long-term human presence. High-energy particles can damage cellular structures and genetic material in living organisms. On Earth, the atmosphere and magnetic field significantly reduce this exposure. But on Mars, the lack of such protection means that any biological system on the surface must rely on artificial shielding. Shielding strategies on the surface involve either physical mass barriers or subsurface placement. Materials such as regolith itself can be used to block radiation when layered above habitats. Even a relatively shallow covering of soil can reduce exposure significantly by absorbing and scattering incoming particles before they reach living or sensitive systems. The Martian surface also experiences secondary radiation effects generated within the soil itself. When high-energy particles strike the ground, they produce cascades of lower-energy particles that propagate through nearby material. This creates a radiation field that is not only external but also partially internal to the surface layer. Solar activity strongly influences radiation intensity at the surface. During periods of increased solar output, bursts of energetic particles can dramatically raise exposure levels for short durations. These events occur irregularly and can reach Mars within hours of emission depending on particle speed. Without rapid shielding response, surface systems may experience temporarily elevated radiation doses. The absence of a global magnetic field means that Mars does not deflect charged particles uniformly. Instead, localized crustal magnetic regions provide limited and uneven protection. These regions create small zones where particle trajectories are altered, producing subtle variations in surface exposure patterns across different geographic areas. Surface geology also reflects long-term radiation exposure. Over extended periods, radiation contributes to the breakdown of complex minerals and the alteration of surface chemistry. This slow process helps explain the oxidized and chemically uniform appearance of much of the Martian terrain, particularly in regions that have remained undisturbed for long durations. Dust on the surface plays a dual role in radiation interaction. While suspended dust in the atmosphere affects light and temperature settled, dust can provide minor shielding when accumulated in layers. However, this effect is limited as thin dust layers offer only partial attenuation of high-energy particles. Human activity on the surface must therefore account for continuous exposure conditions. Unlike environments where protection is intermittent or seasonal, Mars presents a constant baseline of radiation. This requires long-term planning for habitat placement, material selection, and operational timing to reduce cumulative exposure. The surface environment is also shaped by the interaction between radiation and atmospheric remnants. Even the thin carbon dioxide atmosphere contributes slightly to particle scattering, but its protective capacity is minimal. Most energetic particles pass through with little reduction in intensity, maintaining the dominance of radiation at ground level. Over long timescales, the surface represents a slowly evolving system shaped by external energy input rather than internal atmospheric buffering. Radiation temperature and mechanical erosion combine to continuously modify the uppermost layers of the planet, maintaining a dynamic but slow-changing environment. Mars surface radiation thus defines one of the most critical constraints of planetary exploration, shaping both natural processes and engineered survival strategies. It establishes a boundary condition for all surface activity, where exposure is constant and mitigation depends entirely on design rather than environmental protection. Martian regolith forms the immediate interface between the planet's exposed surface and its deeper geological layers. It is a loose, fragmented material produced over immense timescales through impact fragmentation, thermal cycling, and chemical alteration. Unlike cohesive soil systems on Earth, this layer lacks biological structure and is dominated by mineral grains that vary in size from fine dust to small rock fragments. The regolith extends unevenly across the planet, shaped by wind transport, ancient volcanic activity, and repeated meteorite impacts. In some regions, it forms deep deposits that can reach several meters in thickness, while in others, bedrock lies closer to the surface. This variability creates a patchwork of mechanical properties that influence both natural processes and engineering considerations for surface operations. Compositionally, Martian regolith is rich in basaltic material reflecting the volcanic history of the planet. Iron-bearing minerals dominate its color and chemical behavior, producing the characteristic reddish appearance seen from orbit. Over time, exposure to atmospheric oxidants and radiation has further altered these minerals, increasing the prevalence of oxidized compounds. One of the most notable chemical components of Martian soil is the presence of perchlorates. These chlorine-oxygen compounds are stable under current surface conditions, but become chemically active under heat or specific environmental triggers. Their distribution across the planet is not uniform, suggesting formation processes influenced by atmospheric chemistry and long-term surface interactions. The fine grain size of much of the regolith allows it to behave almost like a fluid under certain wind conditions. During periods of sustained airflow, particles can be lifted, transported, and redeposited across vast distances, This mobility contributes to the smoothing of terrain features over time and the redistribution of surface materials between regions. Below the surface layer, regolith gradually transitions into more consolidated material and eventually into solid bedrock. This transition is not abrupt but occurs over depth as compaction increases and fractures become less frequent. The mechanical strength of the ground increases with depth, reducing its susceptibility to wind-driven disturbance. Thermal properties of regolith play an important role in shaping surface conditions. The loose structure of the upper layer allows it to heat and cool rapidly in response to sunlight. This creates strong temperature gradients between day and night, which in turn contribute to physical breakdown of rocks through repeated expansion and contraction. Dust within the regolith is extremely fine, often measuring at microscopic scales. These particles can remain suspended in the atmosphere once disturbed and contribute to long-term atmospheric dust loading. Their small size allows them to interact strongly with radiation, influencing both surface temperature and atmospheric opacity during storm events. Mechanical interactions with regolith are influenced by its cohesion and electrostatic properties. In the low-pressure environment of Mars, dust particles can acquire static charges that cause them to adhere to surfaces. This behavior affects equipment exposed to the environment, as dust accumulation can occur even without strong wind activity. The absence of organic material distinguishes Martian regolith from terrestrial soil. On Earth, biological processes continuously modify soil structure and chemistry, but on Mars changes occur primarily through physical and chemical processes. This results in a slower, more gradual evolution of surface material properties. Regolith also acts as a record of planetary history. Layered deposits contain evidence of past environmental conditions, including variations in atmospheric density, volcanic activity and impact frequency. These layers are preserved due to the absence of active erosion systems comparable to those on Earth. At greater depths, regolith transitions into permafrost regions in some areas where ice is mixed with soil particles. These subsurface layers are influenced by temperature stability and seasonal changes in atmospheric pressure, which can cause limited exchange of volatiles between the surface and subsurface environment. The interaction between regolith and radiation is continuous. High-energy particles penetrate the upper layers and gradually alter mineral structures. Over long periods, this process can change the chemical composition of exposed soil, contributing to the oxidized and chemically stable nature of the surface. Surface operations on Mars must account for the unpredictable mechanical behavior of regolith. Its loose structure can shift under load, while buried rocks and uneven density distributions can affect stability. These properties make interaction with the ground complex despite its seemingly uniform appearance. Wind-driven erosion of regolith contributes to the formation of dunes and ripple-like structures across the planet. These formations move slowly over time, driven by seasonal wind patterns and atmospheric density variations. They represent one of the most dynamic visible aspects of the Martian surface. Regolith therefore functions as both a product and a driver of planetary processes. It reflects the cumulative effects of geological history while actively participating in ongoing atmospheric and surface interactions. Its presence defines much of the physical character of Mars at accessible depths. Near-surface water ice on Mars exists in a fragile balance controlled by temperature, pressure, and seasonal atmospheric changes. At the shallow subsurface level, water ice is not liquid under current conditions, but remains frozen within soil pores or as discrete lenses embedded in regolith. Its presence is not uniform across the planet, instead concentrated in regions where long-term thermal stability allows it to persist without sublimation into vapor. The uppermost surface layer of Mars is generally too warm and too exposed for stable ice to survive for long periods. Even in cold regions, direct sunlight and low atmospheric pressure encourage ice to slowly transition into vapor. This process occurs without melting since liquid water is unstable under most surface conditions. As a result, ice tends to retreat below the surface where it is shielded by insulating material. At shallow depths, temperature becomes more stable and less influenced by daily fluctuations. The regolith above acts as a protective layer, reducing heat exchange between the surface and subsurface. In these conditions, water ice can remain preserved for extended timescales, slowly responding to seasonal or long-term climate variations rather than immediate surface changes. The distribution of near-surface ice is closely linked to latitude. Closer to the poles, colder conditions allow ice to exist nearer to the surface, sometimes only a short distance beneath the regolith. Toward the equator, higher temperatures push stable ice deeper underground where insulation prevents sublimation. This latitudinal pattern reflects the balance between solar heating and subsurface thermal conduction. Seasonal cycles influence the behavior of near-surface ice even when it remains solid. During warmer periods, the upper boundary of ice-rich layers can experience slight sublimation, releasing water vapor into the atmosphere. This vapor can later recondense in colder regions, creating a slow exchange cycle between subsurface reservoirs and atmospheric moisture. The Martian atmosphere contains only trace amounts of water vapor, but even these small quantities play a role in subsurface processes. Vapor diffusion through porous soil allows limited transport of water molecules, contributing to gradual redistribution of ice over long periods. This process is extremely slow, but continuous, shaping the long-term stability of subsurface ice deposits. In some regions, near-surface ice is mixed with dust and regolith to form ice-cemented ground. This material behaves differently from pure ice, or dry soil, exhibiting increased cohesion and altered mechanical properties. The presence of ice strengthens the ground structure, but also makes it sensitive to temperature changes that can trigger sublimation-driven collapse. Orbital observations have identified areas where seasonal changes in hydrogen signatures suggest the presence of shallow subsurface ice. These signatures are detected through variations in neutron flux measurements, which respond to the presence of hydrogen-rich materials beneath the surface. Such indirect detection methods provide insight into ice distribution without direct sampling. The stability of near-surface ice is also influenced by obliquity changes over long timescales. Mars experiences variations in its axial tilt that alter the distribution of solar energy across the planet. During periods of higher tilt, polar regions may become warmer, while mid-latitudes experience shifts in ice stability zones. These long-term cycles contribute to historical movement of ice deposits across the planet. When exposed to sudden changes in environmental conditions, near-surface ice can undergo rapid sublimation. This process can create voids within the regolith, leading to collapse or surface subsidence. Such features may appear as pits or irregular terrain formations, reflecting the hidden presence of ice that has been removed over time. The interaction between ice and regolith also influences thermal conductivity. Ice-rich soil conducts heat more efficiently than dry dust, altering local temperature profiles. This can create feedback loops where heat transfer accelerates sublimation or stabilizes ice depending on local conditions. Dust coverage plays a significant role in protecting subsurface ice. A thin layer of dust can act as an insulating barrier, reducing heat penetration and slowing sublimation rates. Over time, dust accumulation can therefore help preserve ice deposits even in regions that would otherwise be too warm for long-term stability. At slightly greater depths, ice becomes more stable and less affected by surface variations. Here it exists in a state of long-term equilibrium, with surrounding temperatures changing only in response to slow climatic shifts rather than seasonal cycles. These deeper layers represent more persistent reservoirs of water on the planet. The presence of subsurface ice has implications for planetary evolution. It suggests that water has migrated and been redistributed over geological timescales, moving between atmospheric surface and subsurface reservoirs. This cycle reflects a long-term exchange system, operating under conditions very different from those on Earth. Near-surface ice thus forms a hidden layer of the Martian environment existing beneath the visible landscape, but playing a crucial role in thermal, mechanical, and chemical processes. It represents one of the most significant subsurface components of the planet's shallow crust. Deep subsurface ice on Mars exists in a more stable and protected environment than near-surface deposits preserved beneath layers of regolith that insulate it from daily and seasonal temperature fluctuations. At these depths, temperature changes become extremely gradual, and environmental conditions approach long-term equilibrium states governed primarily by internal heat flow and slow climatic variation, rather than direct solar influence. As depth increases, pressure from overlying material gradually compacts the regolith, reducing pore space and limiting the movement of gases and vapors. This compaction helps stabilize ice by restricting sublimation pathways, allowing water molecules to remain trapped within the soil matrix for extended periods. In many regions, ice is not present as pure solid layers, but as mixtures with soil grains forming ice-rich permafrost-like structures. The stability of deep subsurface ice depends strongly on temperature gradients within the crust. Even though Mars is geologically inactive compared to Earth, it still retains residual internal heat from its formation. This heat slowly moves outward, creating a weak but continuous geothermal gradient. At shallow depths, this influence is minimal, but deeper layers begin to reflect this internal thermal contribution. In regions where ice exists at depth, it can persist for extremely long time scales, potentially spanning millions of years with minimal alteration. These reservoirs are effectively sealed from direct atmospheric exchange, making them distinct from near-surface ice that undergoes seasonal sublimation cycles. The deeper the deposit, the more isolated it becomes from surface-driven changes. The mechanical properties of deep ice-rich layers differ significantly from dry regolith. Ice acts as a cementing agent, binding particles together and increasing structural cohesion. This creates subsurface layers that are more rigid and less prone to shifting under external forces. However, changes in temperature or pressure can still alter these properties over long periods. Detection of deep subsurface ice relies on indirect observational techniques. Radar sounding from orbit can penetrate the upper layers of the planet and reveal reflections consistent with dielectric contrast between dry material and ice-rich deposits. These signals provide information about subsurface structure without requiring physical excavation. The distribution of deep ice is influenced by ancient climate cycles. Mars has experienced long-term variations in axial tilt that significantly alter its climate over tens of thousands to millions of years. During periods of higher tilt, water vapor can migrate from polar regions toward lower latitudes where it becomes trapped in subsurface layers as temperatures decline again. This process leads to buried ice deposits far from current polar caps. In addition to climate-driven migration, impact events have also contributed to subsurface ice distribution. Large impacts can fracture the crust and redistribute volatile materials, burying ice beneath ejecta blankets or exposing deeper layers that later become recovered by dust. Over time, these processes create complex subsurface layering patterns. Deep subsurface ice is thermally insulated by overlying regolith, which reduces energy exchange with the surface. This insulation allows temperature at depth to remain relatively constant even during extreme surface fluctuations. As a result, ice at these depths does not experience the same sublimation pressures as shallower deposits. Chemical interactions within deep ice layers are slow but not entirely absent. trace amounts of dissolved minerals and trapped gases can migrate within the ice matrix over long timescales, leading to gradual chemical evolution. However, the absence of liquid water under current conditions limits the extent of chemical processing compared to Earth's subsurface environments. The presence of deep ice also influences the mechanical stability of the crust. Ice-rich layers can affect how the ground responds to stress, including impacts and tectonic adjustments. Although Mars lacks active plate tectonics, localized stress from impacts or thermal contraction can still propagate through these layers, creating fractures or deformation zones. In certain regions, deep ice may be overlain by dry layers that have accumulated over time through dust deposition and erosion. These protective layers act as a seal, preserving underlying ice from direct exposure. The thickness of this protective cover determines how well the ice remains isolated from surface conditions. The potential for deep subsurface ice to persist over geological timescales makes it an important component of Mars' hydrological history. It represents a long-term storage mechanism for water-preserving evidence of past atmospheric conditions and climatic transitions that differ significantly from the present environment. Thermal modeling suggests that some deep ice deposits may remain stable even under current climate conditions for extended durations, provided they remain sufficiently buried. This stability highlights the importance of depth as a controlling factor in the preservation of volatile materials on the planet. Deep subsurface ice therefore forms a hidden reservoir within the Martian crust, largely isolated from active surface processes, yet still shaped by ancient environmental cycles. It exists as a slow, stable archive of planetary water history, embedded within the deeper structure of the planet's geological framework. Lava tubes on Mars form beneath ancient volcanic regions where flowing molten rock once moved through subsurface channels, leaving behind hollow conduits after cooling and solidification. These structures are part of a broader volcanic landscape that reflects a period when Mars was more geologically active, with large-scale eruptions shaping vast areas of the crust. Once the outer layers of lava cooled while the interior continued to flow, empty channels remained, creating long underground cavities. These tunnels vary in size, ranging from narrow passageways to enormous voids capable of spanning many meters in width and height. Their dimensions depend on the viscosity of the original lava eruption duration and slope of the terrain. Over time, the structural integrity of the tube depends on the strength of the surrounding rock and the absence of collapse due to impacts or seismic stresses. The surface above lava tubes often shows subtle signs of their presence. Linear depressions, collapsed pits, and chain-like crater formations can indicate where sections of the roof have weakened or fallen inward. These features provide indirect evidence of subsurface voids that remain otherwise hidden beneath the regolith. Inside lava tubes, environmental conditions differ significantly from the exposed Martian surface. Temperature fluctuations are reduced because thick rock layers provide insulation from external thermal cycles. While not completely stable, these environments experience far less extreme variation than open surface terrain, creating more consistent internal conditions. Radiation levels within lava tubes are also reduced compared to the surface. The surrounding rock acts as a natural barrier that absorbs and scatters high-energy particles from space. This shielding effect makes these environments significantly less exposed to cosmic and solar radiation, although not entirely free from it. The geometry of lava tubes creates long enclosed corridors where light does not naturally penetrate. Without direct illumination, internal regions remain in permanent darkness unless artificially lit. This absence of sunlight preserves temperature stability but also isolates internal environments from surface-driven thermal effects. Some lava tubes may extend for many kilometers, forming interconnected networks beneath volcanic plains. These networks reflect the scale of past volcanic activity, where sustained eruptions produced extensive subsurface flow systems. The continuity of these structures depends on whether the original lava channels remained open long enough before solidification. Over geological time, structural changes can occur within lava tubes due to seismic activity, meteorite impacts, or gradual weakening of rock layers. Sections of the roof may collapse, creating skylights that connect the surface with the subsurface voids. These openings allow limited exchange of material and energy between the two environments. Dust and regolith can accumulate within lava tubes through collapsed entrances or wind-driven transport. However, the rate of accumulation is significantly lower than on the surface, allowing many sections of these structures to remain relatively clear over long periods. This preserves their internal geometry and stability. Temperature within lava tubes is influenced primarily by geothermal heat and insulation from external cycles. While Mars has low internal heat compared to Earth, the absence of direct atmospheric exposure allows these subsurface environments to maintain more moderate thermal conditions than the surface. The structural stability of lava tubes depends on rock strength and gravitational loading. Mars's lower gravity reduces stress on structural spans, compared to Earth, potentially allowing larger stable voids to exist. However, long-term stability still depends on rock composition and the absence of destabilizing events. From a geological perspective, lava tubes represent preserved records of volcanic processes. Their shapes and internal features reflect flow dynamics, cooling rates, and eruption characteristics that occurred during Mars' volcanic past. Studying these structures provides insight into the planet's thermal and geological evolution. In the context of subsurface environments, lava tubes represent one of the most naturally protected spaces on Mars. Their combination of radiation shielding thermal stability and structural enclosure distinguishes them from surrounding regolith and ice-rich layers. These underground cavities form part of the broader hidden architecture of Mars, where geological processes have created layered and interconnected subsurface systems. They remain largely isolated from surface conditions, preserving internal environments that evolve slowly over time. Lava tubes thus function as long-lasting geological voids shaped by ancient volcanic activity, persisting beneath the planet's surface as silent structural remnants of a more active planetary past. Surface habitat construction on Mars begins with the fundamental constraint that the environment offers no natural protection from radiation, extreme temperature variation, or atmospheric instability. Any permanent structure must therefore act as an artificial extension of planetary shielding, replacing the functions normally provided by a dense atmosphere and magnetic field on Earth. The outermost layer of a habitat is not decorative or optional, but forms the primary barrier between human systems and continuous environmental exposure. One of the most effective approaches to shielding involves the use of local regolith. Martian soil, when compacted into thick layers above living spaces, provides significant attenuation of high-energy particles. This method reduces radiation exposure by increasing the amount of mass that incoming particles must pass through, dispersing their energy before it reaches inhabited areas. The effectiveness of this shielding depends directly on thickness and uniformity of coverage. Structures built beneath the surface offer additional protection. Excavation into natural terrain or construction within subsurface formations allows habitats to be embedded within the planet itself. In such configurations, surrounding rock becomes a passive shield, reducing both radiation levels and thermal fluctuations. This approach takes advantage of Mars's geological material rather than relying solely on imported construction elements. Where surface construction is necessary, habitats often rely on layered systems. External shells are designed to withstand temperature cycling and micrometeorite impacts, while internal layers regulate pressure, temperature, and air composition. These systems must maintain a stable internal environment despite external conditions that fluctuate widely over time. The thin Martian atmosphere provides minimal pressure support, meaning that all habitats must be fully pressurized structures. Internal pressure is maintained at levels suitable for human physiology, creating a strong pressure gradient across structural walls. This gradient imposes constant mechanical stress that must be managed through careful engineering and material selection. Thermal regulation within habitats is equally critical. The external environment can shift from extremely cold conditions during night to significantly warmer conditions during daylight exposure. Without atmospheric buffering, these changes occur rapidly, requiring internal systems to actively stabilize temperature through controlled heat exchange and insulation. Dust infiltration is another major consideration. Fine particles suspended in the Martian environment can enter structures through minimal openings and accumulate on surfaces. Once inside, dust can affect mechanical systems, optical equipment, and air filtration units. Habitat design therefore emphasizes ceiling filtration and controlled entry points to limit contamination. Radiation shielding within habitats is not uniform across all areas. Certain sections, such as sleeping quarters or long-duration occupancy zones, often receive additional protection compared to work or transit areas. This creates spatial variation in shielding intensity within a single structure, reflecting differing exposure requirements. The use of inflatable or modular structures has been considered for initial deployment phases due to ease of transport and expansion. However, such structures still require external shielding once deployed, as their material alone is insufficient to block high-energy radiation. This reinforces the importance of integrating local materials into habitat design. Power and life support systems are embedded within habitat infrastructure, requiring redundancy to maintain stability under all conditions. These systems regulate oxygen levels, remove carbon dioxide, recycle water, and maintain air pressure. Their operation is continuous and tightly controlled, as any failure in closed environments can rapidly compromise habitability. Communication systems link habitats to orbital stations and Earth, but the delay in signal transmission means that operational independence is essential. Habitats must function autonomously for extended periods, relying on onboard monitoring and automated response systems to maintain safety and environmental control. External access points represent one of the most vulnerable parts of any habitat system. Airlocks must manage transitions between pressurized and unpressurized environments, while minimizing loss of internal atmosphere. These systems are designed with multiple safety barriers to prevent rapid decompression. Human activity outside habitats requires protective suits that replicate internal habitat conditions. These suits must provide pressure oxygen, thermal regulation, and radiation reduction within a portable system. Movement in such suits is physically demanding, further emphasizing the importance of minimizing external exposure duration. The placement of habitats often considers natural terrain features such as cliffs, crater rims, or subsurface voids. These locations can offer partial natural shielding and reduce the amount of artificial material required for protection. Environmental stability is a key factor in selecting long-term settlement zones. Habitat construction on Mars therefore exists at the intersection of engineering and environmental constraint. Every structural choice reflects an attempt to recreate stable Earth-like conditions within a planet that does not naturally support them. The surrounding environment remains constant in its hostility, requiring continuous adaptation from all artificial systems. Within this framework, surface habitats function as isolated pockets of controlled atmosphere, embedded within a larger planetary system that remains fundamentally uninhabitable without technological mediation. Closed-loop life support systems on Mars function as self-contained environmental cycles that continuously recycle air, water, and nutrients to sustain human life in an isolated planetary setting. These systems operate because no external replenishment is naturally available in sufficient quantities, making internal regeneration the only viable long-term solution. Every component is interconnected, so the stability of one cycle directly influences the others. Air recycling begins with the continuous removal of carbon dioxide produced by human respiration. In a sealed habitat, carbon dioxide concentration would gradually rise without intervention, eventually becoming harmful. Life support systems therefore use chemical and physical processes to extract carbon dioxide from the air and convert it back into breathable oxygen. This conversion relies on controlled reactions in electrochemical systems that maintain atmospheric balance. Oxygen generation is closely tied to water management. Water molecules contain hydrogen and oxygen, and through controlled processes, oxygen can be separated and reused for respiration. Hydrogen is often retained within the system to support other chemical processes or combined with carbon dioxide recycling pathways. The interdependence of these elements ensures that no single resource is treated as isolated or expendable. Water recycling is one of the most critical aspects of closed-loop systems. In a Martian habitat, water is continuously recovered from multiple sources, including human consumption, humidity in the air, and waste processing. Filtration and purification systems remove contaminants at molecular and microbial levels, returning water to a usable state. This cycle repeats continuously, minimizing the need for external water input. Waste management is integrated into the recycling system rather than treated as a separate process. Organic waste is broken down into simpler compounds through controlled decomposition and processing systems. The resulting materials are then reused within the habitat's resource cycles, contributing to water and nutrient recovery. This reduces accumulation and supports long-term sustainability. Food production within closed-loop systems often relies on controlled agricultural environments. Plants grown in artificial lighting or carefully regulated sunlight conditions serve multiple roles, including oxygen, production, carbon dioxide absorption, and food supply. Growth conditions are tightly controlled to match atmospheric composition, temperature, and humidity requirements. Nutrient cycling is essential for sustaining plant life in enclosed systems. Essential elements such as nitrogen, phosphorus, and potassium are recovered and redistributed through biological and chemical processes. Without this recycling, nutrient depletion would occur quickly, making long-term cultivation impossible. These cycles mirror in simplified form the nutrient flows found in natural ecosystems on Earth. Atmospheric control systems regulate pressure, humidity, and gas composition within habitats. Sensors continuously monitor changes while automated systems adjust flow rates to maintain stable conditions. Even small deviations in oxygen or carbon dioxide levels must be corrected quickly to prevent long-term imbalance. Heat generated within habitats from human activity and electronic systems must also be managed. Thermal control systems distribute excess heat or retain warmth depending on environmental needs. In the absence of a natural atmospheric buffer, temperature regulation becomes entirely dependent on engineered systems that actively maintain equilibrium. Microbial management plays a hidden but important role in closed environments. Microorganisms can exist in air, water, and surfaces, and their populations must be controlled to prevent harmful growth. At the same time, some microbial processes are beneficial and are used in waste breakdown and nutrient cycling. The balance between control and utilization is carefully maintained. System redundancy is essential because failure in any major subsystem can quickly cascade through the entire habitat environment. Backup units, parallel systems, and automated fail-safes are used to ensure continuous operation even under partial system failure. This layered design reflects the absence of external rescue or replenishment options. Resource efficiency defines every aspect of closed-loop design. Unlike Earth, where natural cycles continuously replenish resources, Martian habitats must operate with minimal loss. Even small inefficiencies accumulate over time, making precision and conservation fundamental principles of system design. Human interaction with these systems is limited to monitoring, maintenance, and occasional correction. Most processes operate autonomously, guided by continuous sensor feedback. This reduces the risk of human error while ensuring that environmental stability is maintained even during periods of inactivity or sleep cycles. Closed-loop life support systems therefore represent a complete recreation of basic environmental functions within an artificial boundary. They replace atmospheric exchange, hydrological cycles, and biological recycling with engineered equivalents that must function continuously without interruption. Within the Martian context, these systems form the invisible foundation of survival, maintaining stable internal conditions against an external environment that remains entirely incompatible with unprotected human life. Energy generation on Mars exists as a continuous requirement rather than an optional support system, because every aspect of habitat survival depends on stable and uninterrupted power. Without a dense atmosphere or accessible large-scale fossil resources, energy must be produced through engineered systems that convert sunlight, nuclear decay, or stored chemical potential into usable electricity and heat. These systems operate under environmental constraints that include dust, accumulation, temperature variation, and limited maintenance opportunities. Solar energy is one of the primary sources available on the Martian surface. Sunlight reaches the planet with reduced intensity compared to Earth due to greater distance from the Sun, but it remains sufficient for electrical generation through photovoltaic systems. These systems convert incoming light into electrical current using semiconductor materials that respond to photon energy. Their performance depends strongly on surface exposure and cleanliness. Dust accumulation on solar panels presents a significant operational challenge. Fine particles carried by wind or deposited during global atmospheric events can gradually reduce the amount of light reaching active surfaces. Over time, this accumulation decreases energy output, requiring either mechanical cleaning systems or passive mitigation strategies such as angled panel design or electrostatic repulsion techniques. Seasonal variation affects solar energy availability. Mars experiences changes in distance from the Sun due to its elliptical orbit, leading to fluctuations in received solar energy throughout the year. During periods of reduced sunlight, energy systems must compensate by relying on stored reserves or alternative generation methods to maintain habitat stability. Nuclear energy provides a more stable and continuous power source that is less dependent on environmental conditions. Small modular nuclear systems generate heat through controlled radioactive decay processes, which is then converted into electricity. These systems are particularly valuable during dust storm events or extended periods of reduced solar exposure when surface illumination becomes unreliable. Thermal management is closely integrated with energy production systems. Waste heat generated by power conversion processes must be distributed or stored to prevent system overheating. In the cold Martian environment, some of this heat can be repurposed for habitat warming, reducing overall energy waste and contributing to internal temperature regulation. Energy storage systems play a critical role in balancing supply and demand. Batteries and other storage technologies accumulate excess energy during periods of high generation and release it during periods of low production. These systems must operate efficiently under extreme temperature conditions, requiring insulation and thermal stabilization to maintain performance. Power distribution within a habitat is carefully managed to prioritize essential systems. Life support atmospheric control and communication systems receive continuous power allocation, while non-essential systems may be temporarily reduced during energy shortages. This hierarchical distribution ensures that critical functions remain stable even under constrained conditions. Electrical infrastructure must also account for the effects of radiation on electronic components. High-energy particles can disrupt electrical circuits, degrade materials, and introduce errors in data transmission. Shielding and redundancy are used to minimize these effects, ensuring that energy systems remain reliable over long durations. Autonomous monitoring systems continuously assess energy production and consumption. These systems adjust operational loads, activate backup generators, and redistribute power as needed without requiring constant human intervention. This autonomy is essential in an environment where communication delays prevent immediate external support. The integration of energy systems with habitat infrastructure creates a tightly coupled network where production, storage, and consumption are interdependent. A failure in one component can affect multiple systems, making redundancy and isolation mechanisms critical to overall stability. In remote or early-stage Martian settlements, energy limitations directly influence the scale of human activity. Available power determines the extent of scientific operations, construction efforts, and resource processing capabilities. Energy abundance or scarcity thus shapes the pace of expansion and sustainability of presence on the planet. Environmental conditions can also influence nuclear and electrical systems. Extreme cold affects battery chemistry and material performance, while dust can interfere with cooling systems or mechanical components. These factors require continuous adaptation in system design to ensure reliability under variable conditions. Energy generation systems therefore function not only as technical infrastructure, but also as environmental stabilizers within habitats. They regulate temperature indirectly, maintain atmospheric systems, and support all forms of human activity, forming the backbone of operational continuity. Within the Martian environment, energy is not simply produced but carefully balanced across multiple interacting systems that must remain synchronized despite external instability and internal demand fluctuations. Human physiology and Martian gravity unfolds as a slow and continuous adjustment to a gravitational field that is weaker than Earth's, but still strong enough to shape every movement of the body. Mars has roughly 1/3 of Earth's gravity, which alters the way muscles, bones, fluids, and sensory systems function over time. This change does not cause immediate failure, but it gradually shifts how the body maintains structure and balance. The skeletal system responds first to reduced loading conditions. On Earth, constant gravitational force helps maintain bone density through continuous mechanical stress. On Mars, this stress is significantly reduced, leading to slower bone maintenance processes. Over extended periods, bone tissue adapts to lower demand, gradually decreasing density, unless countermeasures are applied through exercise and mechanical resistance. Muscle systems undergo similar adaptation. Muscles that normally support posture and movement against stronger gravity experience reduced workload. Without regular exertion, muscle fibers gradually reduce in strength and volume. This process is not uniform, as different muscle groups respond differently depending on their function in movement and stabilization within reduced gravity. Fluid distribution in the human body also shifts under Martian gravity. On Earth, gravity helps maintain a balanced distribution of blood and bodily fluids. In lower gravity, fluids tend to redistribute toward the upper body, altering pressure dynamics within the circulatory system. This affects cardiovascular regulation and can lead to gradual physiological adaptation as the body attempts to restore internal balance. The cardiovascular system adjusts to reduced resistance in pumping blood. Over time, the heart may operate under different load conditions compared to Earth, altering its efficiency and structural characteristics. These changes are gradual but become more pronounced with extended exposure to low-gravity environments. Balance and orientation rely heavily on the vestibular system, which interprets motion and spatial position. In reduced gravity, the signals received by this system change, leading to altered perception of movement and stability. The brain gradually recalibrates these signals to match the new gravitational context, adjusting coordination and spatial awareness. Movement on the Martian surface requires adaptation to both gravity and environmental constraints. Walking, lifting, and climbing all feel different under reduced weight conditions. While objects are easier to move in terms of force-required inertia, still governs motion, meaning that once movement begins, it must be carefully controlled to avoid overshooting or instability. Respiratory function is influenced indirectly by atmospheric conditions within habitats, rather than external gravity. Pressurized environments maintain breathable air, but reduced gravity can still affect lung mechanics and airflow distribution within the body. These effects are subtle but contribute to overall physiological adaptation. The absence of a natural Earth-like day-night cycle in controlled habitats further influences human biology. Artificial lighting and regulated schedules replace natural sunlight rhythms, affecting sleep cycles and hormonal regulation. Over time, the body adjusts to these artificial patterns, but the transition requires careful synchronization of environmental cues. Radiation exposure remains a constant background factor affecting physiological systems. High-energy particles can interact with biological tissue, increasing the importance of shielding and limiting exposure duration. While habitats reduce this exposure significantly, it is not completely eliminated, making long-term adaptation a key consideration. Exercise becomes a critical countermeasure to physiological changes. Controlled physical activity is used to simulate gravitational stress on muscles and bones, helping maintain structural integrity. Without such interventions, long-term exposure to reduced gravity environments would lead to progressive weakening of the musculoskeletal system. Psychological adaptation also plays a role in physiological stability. The body and mind are closely linked, and changes in environment, isolation, and sensory input influence hormonal balance and stress regulation. These effects are gradual but significant in long-duration missions. Sleep patterns in reduced gravity environments may shift due to altered body positioning and environmental cues. The absence of natural gravitational compression changes how the body rests, requiring carefully designed sleeping environments to maintain comfort and stability. Temperature regulation within habitats ensures that physiological systems are not stressed by external environmental extremes. However, the body still adapts to artificial climate control, which differs from natural Earth variability. This stable environment reduces certain stresses while introducing new forms of long-term adaptation. Over extended periods, human physiology in Martian gravity becomes a system adjusted to lower force conditions, altered fluid dynamics, and continuous environmental control. These changes reflect the body's ability to adapt within engineered environments, but they also highlight the dependence on external systems to maintain long-term stability. Within this context, human presence on Mars is not static but continuously adaptive, shaped by the interaction between biology and a fundamentally different gravitational and environmental framework. Psychological isolation on Mars emerges as a gradual and persistent condition, shaped by distance, environmental confinement, and the absence of immediate earthly reference. The human mind adapted to continuous social and ecological feedback. On Earth enters a setting where external cues become limited, communication is delayed, and sensory environments are carefully controlled. This combination creates a cognitive landscape defined by reduced novelty and extended temporal separation. The delay in communication between Mars and Earth introduces a structural separation in interaction. Messages require minutes to travel in each direction due to the finite speed of light and planetary distance. This delay prevents real-time conversation and replaces it with asynchronous exchange where responses arrive detached from the immediate context in which they were generated. Over time, this alters expectations of interaction and decision-making. Living environments on Mars are enclosed systems where external sensory input is limited. Visual landscapes remain static compared to Earth's dynamic ecosystems. There are no natural winds carrying organic scents, no flowing water systems shaped by continuous weather cycles, and no biological diversity evolving in real time around daily life. The environment becomes stable, controlled, and predictable, which reduces sensory variation over long durations. The absence of Earth's natural ecological complexity affects cognitive stimulation. On Earth, constant environmental change supports attention cycles through subtle variation in sound, light, and motion. On Mars, these variations are largely engineered rather than naturally occurring. This shift can influence perception of time, as repetitive environments may cause days to feel structurally similar, even when chronologically distinct. Social dynamics within Martian habitats are constrained by limited population size and spatial confinement. Human interaction occurs within a small continuous group, where privacy and separation are reduced compared to Earth environments. Over time, this can intensify awareness of interpersonal behavior and increase sensitivity to social patterns within the group. Sleep cycles are influenced by artificial lighting systems designed to simulate Earth-like day-night rhythms. However, the absence of natural sunrise and sunset transitions reduces external anchoring of time perception. The body adapts to scheduled lighting, but internal biological rhythms may still experience subtle desynchronization, requiring careful environmental regulation. Cognitive workload in Mars environments includes constant awareness of system dependency. Every aspect of survival relies on monitored infrastructure from air composition to power stability. This creates an ongoing background awareness of system integrity even during routine activities. Over time, this awareness becomes integrated into normal cognitive processing rather than remaining a distinct concern. Emotional regulation is influenced by the combination of isolation, environmental monotony, and operational responsibility. The mind adjusts by developing routines and internal stabilization mechanisms that reduce stress response variability. These adaptations occur gradually and vary between individuals depending on psychological resilience and support systems. The perception of distance from Earth is not only physical but also experiential. Earth becomes a conceptual presence rather than a direct environment. Its changing conditions are known only through delayed information, making it less immediate in daily awareness. This transformation alters the psychological weight of terrestrial connection over time. Environmental control systems within habitats maintain stable temperature, pressure, and atmospheric composition. While this stability is essential for survival, it also reduces exposure to natural variability that typically engages human sensory adaptation. The result is a consistent environment that supports life but limits spontaneous environmental change. Time perception in Mars habitats becomes structured primarily by operational schedules rather than natural cycles. Work, rest, and maintenance are organized into precise intervals to maintain system stability. This structured rhythm replaces organic environmental timing and gradually shapes cognitive expectation of daily progression. Despite these constraints, adaptation occurs as the human mind reorganizes its relationship with space-time and environment. Familiar patterns form within the habitat, and routine activities create a stable internal framework that supports psychological continuity. Over time, the environment becomes normalized rather than constantly perceived as alien. The combination of isolation, environmental control, delayed communication, and confined social structure defines psychological experience on Mars as a steady adjustment rather than a sudden shift. The mind adapts by integrating these conditions into its baseline perception of reality, maintaining function within a fundamentally altered world. Within the broader context of Martian colonization, psychological adaptation represents the final layer of survival systems complementing physical engineering and biological adjustment. It completes the transition from Earth-dependent existence to sustained presence in an entirely separate planetary environment